sort of in double integral. We've done it. And so I'm gonna say, well, the same thing with the triple integral. Then we talk about the moments and center of mass. Every assignment on this, except for the worksheet, has worksheet 12 has one question on this that is not an extra credit, but the web assign on this section is completely extra credit. Is easy. Okay. Okay, so here's what we used to do. We would talk about like a lamina that it's the two-dimensional region, right? Lamina is a two-dimensional region like that in the XY plane. And we sort of explained this in before, that if the lamina has density function, so the mass density, that means that at point X and Y on the lamina, you can, if you have an infinitesimal little rectangle around it, you will get basically that infinitesimal rectangle area in this mass density of the unit of mass over units of area. Well, we're saying that it's a lamina, right? It's just the we need a volume, but if we're assuming a small height the same, or you can even assume that if the height is changing a tiny bit, it's counted in the mass density function. So that basically, that little piece of the lamina around X and Y, the mass density function times delta X delta Y gives you the mass, the small mass. Why am I all blue? Gives you the small mass, right? And then you basically, you go from there back to the lamina. I'm trying, these two shapes are the same. I just couldn't draw them the same. And so if you do the same, the Riemann something again, you basically adding up all these little the values. And so you get the entire mass is the sum of those little masses, is approximated by sum of those little masses. And so here you want to have point. If you remember, it's a sample point. And so you want the sample point mass density function times delta X times delta Y. And you will have I from 1 to M and J from 1 to N. And so you approximate the mass with this, put a limit in front of it, and that will give you the mass. Okay, so that's the general idea of why we're saying that the formula is going to be this. So the mass is going to be the double integral, see, double sum of delta x and y dA, either dx dy or dy dx, right? Over the lambda's name. What was the lambda's name? D. So that becomes the mass. So the mass is the double integral of the density function, dA. And that's what we so far discussed. Similar thing happens. You've been using this without sort of knowing why. This was explanation of why this formula is true. You've been using and we just did the explanation. Vincent, what? Do you have a question? Is that Vincent?
Okay. Oh, sorry.
No, okay. Oh, you just turn on your, you unmuted yourself without knowing, is that it? Okay, that's okay. So now, same thing is true. If I have the mass density function, so if I have for 3D, that was for 2D, for lamina, for 3D, if I have the mass density function at any point in this space for a solid, mass density for a solid, then basically with the similar things, except for the little rectangles, you will have a little cubes and you end up with the mass is going to be equal to, did I use capital M before? No, I wrote mass instead of, it should be little m. Little m is it's going to be the triple integral over the solid, we call the solid S of the density dV. dV is a variation of dx, dy, dz, right? It's the volume element in whatever order. So that said, I want to tell you also, we talk about mass density a lot. The same concept applies if you have the charge density. The same concept applies for whatever density. So you take the double integral or triple integral to get the entire total values, right? So that's the little thing. Let's do one quick question on that. Again, find the mass of the rectangle this when density is this. So what is it? It's just the double integral of the mass density and dA. dA can be dx dy because it's a rectangular shape. It can be either way. If I put in dx first, it's from 0 to 2. Then if I put dy, it's from 0 to 3. Oh, nice, it's rectangular region, so I can basically separate these things.
The x to y squared, the function.
What's that?
The actual function, you got x to y, x and y squared. You got x squared and y.
Oh, thank you. So yes, and the function is a function of x only times function of y only. So I can separate this and write it as that over the rectangular regions. And so the first one is going to be what? The second one, it's easier. This is 0. The first one is this. Then you multiply is 4 divided by 2 times what? 27 divided by 3, and that gives me 2 times 18. Is that right? Yeah. Okay. So 18 kilogram is the mass of the rectangle. What did I do? Okay, my friends, messed up a little bit. So let's clean it up a little bit and move on to the iClicker one. Talk about moments and center of mass. So what is happening with the moments and center of mass? So basically, moments is just gathering up. Let's see, let's talk about moments m sub x. What is happening? There we go. So we're talking about moments of inertia. Inertia, oh goodness, about x-axis. So, okay, so here's the x-axis, here's the y-axis, and I have something, like I have a lamina, right? So what we're doing, x-axis is this one. I should have had a different color. Oh, x-axis is this one, and I want to figure out the inertia, moment of inertia about the x-axis. So what is happening? If you're kind of looking at the rotation about the x-axis, you're basically finding for little pieces on the lamina, little infinitesimal Riemann pieces on the lamina, you're finding the mass of that little piece, and then you multiplying by the distance of that piece to the axle of rotation. But that little piece distance from the axle of its rotation is in the distance is in the y direction. So what you're basically finding is that you're finding the distance. And so the little pieces here are going, if I'm going in the, that doesn't look right. So little piece over there, and I have the x-axis, and I want to find how it rotates about the x-axis. I have to find the little distance from the x-axis, but that would be in the y direction, right? So this is how it works. And so it's m sub x. If you remember the teeter-totter, the distance from the center, that was the one-dimensional situation, right? We're going to two-dimension now. Teeter-totter, the point that you're finding the rotation about, you find the distance from that point, you multiply by the weight, right? And so here we're doing the similar thing, but when we're going about the x-axis, you're basically, wait, let me start y. There we go. You're finding the little y's and times the, by the way, we're in our book, we're using delta for the density function. A lot of books use rho and other sort of things. So just remember that part, right? So that becomes the moment of inertia. And then if I want to find, basically, if I want to find the, hold on, that's for the m sub x. Let me write down m sub y. And for m sub y, it reverses, right? So that's the moment of inertia. But then if I want to find the center of mass, then I'm basically, for x values, I'm finding the m sub y. So if I'm finding the center of mass, let's say center of mass, we call it x bar and y bar. Center of mass has a point, is a point right here. Center of mass is where you have the stability. If you put the entire lamina on top of the center of mass, it's supposed to, and everything can stay, and what do you call that? That it's not falling one way or another.
Static.
Yeah, it's going to be static. It's going to be status, right like that. So to find the center of mass, you basically want to figure out, average out y in terms of their mass. You want to average out for x, you want to average out x's in terms of mass, which is this m sub x over m, which is going to be the double integral x over the region, delta x and y, dA. Where is my handwriting going? There we go. Not a very good place, but okay. So x delta x and y dA divided by the mass, which is going to be r delta x and y dA. So it finally, that now x bar matches with x in the integral, and y bar is going to be m sub y over m, which is y delta x and y dA over delta x and y dA. So again, averaging for the x bar, you're averaging the x. And so you have to get rid of the mass part of it. See, the density function was helping you to average. You have to divide by that density function, and divide by the mass because you use the density function. And for y, you're averaging out y's, and you're dividing by the mass. So basically, that's the part that takes the density function effect out. It's just averaging out y. And so that's the story. Let's do one example. Are you guys ready? It tells you to find the mass and center of mass of a triangular lamina with these points. 0, 0, 1, 0, 1, 0, and 0, 2. So that's the point. And then the density function, the mass density function is that. So I want to find the center of mass. I have to find x bar and y bar. There's a center of mass sitting here, and it has x bar and y bar. And if I put the lamina on top of that, put a little wedge underneath that point, it has to stay balanced, right? Balanced, static, whatever that is called, right? So this is going to be the double integral over this region of x times 1 plus 3x plus y dA over the mass. Oh, I didn't write it as double integral. Are you guys guessing why? Oh, no, I have to. Let's write it as mass because I want to tell you, I want to do it separately because I don't want to do it twice. And this one is going to be y. So This is the average of y. And the other one is the average of x. Okay, seems like the denominator is the same for both of them. So let's find the mass separately. So mass is the double integral 1 plus 3x plus y dA. And that is, let's set up the double integral. Setup is going to be the same for all of them. Let's figure out what this is for this setup. That one is what is that line? Y equal to minus 2x plus 2. Am I right? Right. If I plug in 0 for x, I get 2. If I plug in 1 for x, I get 0. Yeah. So that's the line. Should I do vertical simple or horizontal simple? Let's do vertical. It's already solved for y. So this is going to be, the inner one is going to be from 0 to 2 minus 2x with respect to y. The arrow is y direction. And then the outer one is going to be with respect to x. And x goes from 0 to 1. And then you take the integral. I have no idea why my handwriting is so bad today. There we go. And so that's it's not like everyday thing, right? And so this is going to be y plus 3xy plus y squared divided by 2. And I plug in 0 and 2 minus 2x. And I get, out of this, I'm going to get, for y, I have to plug those in. I get 2 minus 2x plus 3x times 2 minus 2x plus 2 minus 2x to power 2 divided by 2. And you're taking the integral of that. And when I plug in 0, it's basically all 0. 0 to 1 dx. And now I'm cheating because I don't want to calculate that. That's a lot of algebra. 8/3. So now the denominator for both of these are 8/3. Let's find the numerator in each case. And again, I'm going to set it up, but not solve completely. And so the top part, again, I can repeat the same setup I did here. 0 to 2 minus x, 0 to 1, dy dx. And the inner would be x plus, the integrand is going to be x plus 3x squared plus xy over 8/3. And for y bar, we will have again the same setup. Instead of it's y times, so it's going to be y plus 3xy plus y squared dy dx over 8/3. And if you compute, oh, what did I do? I set up the bounds as 2 minus 2x. It has to be exactly the same as that one, right? And so the answer to first one is 3, 8, and 11, 16. 3, 8, and 11 over 16. So there's a point. This is the 3, 8, and 11 over 16. That point over there is that. Okay, questions so far? Are we good? And the next part that I want to discuss, oh, I have one more of these left. I'm changing the order because I want to discuss this and give you a little time to think about the center of mass and everything. How do we expand this to three-dimensional? The objects are three-dimensional, right? Now, in three dimension, you will have the moment of inertia about a plane instead of having it about an axis. So the moments of inertia moments are about XY plane, XZ plane, YZ plane. Okay, and then so the funky part that if I'm doing about XY plane with the same routine that we did for the two dimension, the moment is going to be Z delta XYZ. So basically M XY is going to be the triple integral over the solid that we're computing of Z sigma XYZ dV. Okay, and then M sub XZ similarly, oops, divide, oh, there we go. I'm still doing the moment, right? And similarly for that one, the variable that is missing. My interest in moments are lower. My interests are center of gravity or center of mass is more of my interest. And then what is missing? X. And so, but if you want to find the center of gravity or center of mass, then you do X bar equal to the triple integral over the region, over the solid of X delta X and Y and Z dV divided by the entire mass. If you want to do Y bar, you do triple integral of SY delta dV over the mass. Again, you're averaging out the X's in terms of the weight, the mass density, and you're averaging out the Y's in terms of mass density, and so on and so forth. So that's the formula that I'm giving. You can watch this video about this question. I